So I apologize because this lesson is going to be a little bit longer than your other ones, simply because we're going to talk about three pieces and they go so well together. Neither one of them is very complicated. So we'll put everything together, but this lesson, because there's more slides and it's going to take us a couple extra minutes. Any of you that feel like, why in the heck are we calculating the math? I love this cartoon. I thought it was great when I saw it. I shared it with one of my other classes. Force equals mass times acceleration. Acceleration equals force divided by mass. That goes great with your last lesson. So he's doing the math to figure out, well, from what angle do we need to launch it? Figuring out all the calculations while he's hit in the face. Finishing off with physicists always lose snowball fights. Yes, I know in the real world, you don't sit and do the math, but you use all the concepts that you use when you do the math. And sometimes when we actually stop and think about what the math is, it can help us better understand concepts. I'm hoping by the end, you will understand power, especially horsepower, a little bit better at the end of this lesson than maybe you do right now. It's one of the concepts that I used to always kind of struggle with was we were talking about cars, you talk about torque and horsepower and what did the two of them mean? Now, we're not going to talk about torque in this lesson. We're going to leave torque until we get to gears, but by the end of this lesson, we will talk about power. So we're going to look at work, energy, and power. We're going to start with work. In physics, the concept of work can be a little bit confusing for people. In physics, work is the result of a force that causes a displacement or a change in distance of an object. It has to be in the same direction as the force applied. So you see here, we're pushing a box across the surface. So a car driving down the road. The force that's in the forward direction times whatever the distance is you went will give you the amount of work that was done. Now, I know you guys have looked at a formula that's similar to this, force times distance, but when you use that formula, you use perpendicular distance. And that's when we look at the torque force. We're going to find the torque force is related really closely to the work force, to the work equation. So torque and work are closely related, but the difference with work is that force and direction are in the same direction. They're not perpendicular. It's not going to cause rotation. It's just going to cause something to slide. Okay, so work is always measured in joules. A joule is technically a Newton meter, which Newton meters are, I know, a unit that you've seen before. Displacement or distance, the change in distance, is always measured in meters, and then the force is in newtons, just like before. So what is work done in physics? And I say in physics because if you take it outside of the context of physics, you could think of a lot more scenarios. But in the physics definition, we do work if we push an object for a distance or pull an object for a distance. And if we lift an object to a height. In every case, there has to be some kind of motion happen. If there is no motion occurring, no work is happening. What is not work done in physics? Well, if you push against a wall, your arm will get tired. So that makes you think there's work being done. But in the physics definition, because the wall didn't move, you haven't done any work. That's the physics definition. I know it's a little bit abstract. If you're walking around with an object and you're not changing the height of the object, so like this picture down here, we have somebody, a waiter, and they're carrying around a platter. The distance they're going is horizontal, but their force is upward. Technically, by physics, they're not doing any work. I would not recommend you telling that to anybody that happens to work as a waiter or waitress because it can be exhausting work, I'm sure. I've never done the job. But technically, by physics, it's not work. Sorry if I insulted anybody. I didn't mean to. I'm just simply using the physics definition. And it does help us kind of have a visual of that kind of weird concept that you go, wait a second, that is work. My arm gets tired. But it's just by physics, we're using that definition. The work, the force and the direction of motion always have to be in the same direction. You're not really going to have to worry a whole lot about those definitions. But I wanted to make sure you know what the physics definition of work is. So you'll see some of the specific examples that we use. So we're going to do a couple of calculations. These are really nice, easy calculations because the formulas are really easy to work with. Now, I just seem to have lost my tablet. Regain it here. So the first question asks you how much work is done if an engine applies 1,200 newtons of force to move a car forward 5 meters. So what we need to do is we need to think of our work formula. So going back a couple slides, work equals force times distance. The force and the distance have to be in the same direction. So the engine applies 1,200 newtons of forward force. Oops. So do 1,200 times whatever the distance is it's moved. So we got 5 meters. Newtons always goes with meters, so we match those up. 1,200 times 5 gives us 6,000 joules of force. I said force. 6,000 joules of work. Okay. The next one asks us, oh dear, I have a wrong word in here. I have a word, how much force, and it should be how much energy. I've made a there we go. How much energy is needed to lift a 281 kilogram Corvette engine 1.5 meters with an electric motor? So let's say we're using a lift and we have our engine. I know this doesn't look like an engine, but it works. The diagram works for us. So we're lifting it upwards 1.5 meters. Okay. We want, one of the things we need to figure out, well, what's the force that we're lifting up with? So we're lifting against gravity. So in order to lift up, we have to lift with a force that matches gravity. Remember, Newton's equal and opposite forces. So that's what we have happening here. So first of all, we need to find the force of gravity because that's the force we're lifting against. So force is mass, 281 kgs, times gravity, which is 9.81. Anytime you're lifting an object, the force needed to lift an object will usually match. In your case, it will always match the force of gravity. So it's always going to be this equation. I don't deal with more complex versions with your class simply because of the amount of time. You just kind of need the skim version. Multiplying those two together, we get 2,757 newtons. And then if we want to know, well, how much energy is required, how much, and I've used the word work and energy, well, we'll get there. Let's change here. I'm going to edit. I will go back and I'll edit the PowerPoint, but if I escape now and come back, it just makes solutions. You'll see why I used the word energy before, not work, in the next slide. You'll see there's a connection between the two. So the work is equal to the force applied times the distance that we have moved it. So the force is 2,757 newtons times 1.5 leaves us with, we have done 4,136 joules of work. Okay, so they're not complicated. Yes, you're never going to have to memorize the formulas. You can go back to your notes. Because of the number of formulas in this section, I will, in the final assessment, I'll give you a page with them all kind of summarized together. That doesn't mean you won't have to go back and look for some information, but it'll kind of help you collect it so that you're not maybe scrambling through notes as much depending on what you printed off. So that's work. Work, force times distance. How big my push was times how far I moved it. The further you move the object, the more work that's required. That makes sense. Energy is the ability to do work. It doesn't mean work's getting done, but the ability to do work is there. Energy is required to do work. So work and energy are both measured in joules. And in a mechanical system, the amount of work that's done on an object is equal to the change in kinetic energy. And we're going to find that kinetic energy is the energy due to motion. Okay, so gasoline has the ability to do work. It's got the potential to be changed into something that can do work in a motor, which can in turn move a car. We take gasoline, which is a source of energy, and we're changing it into kinetic energy. Okay, the energy, if we had 100% conversion, which I know you guys know that that's not true. If we had 100% conversion, the work done or the amount of energy we extract from the gas would be equal to the change in kinetic energy or equal to the work done by the car. So one quick definition that we need to have is or a law that we need to know. And it's just one of those principles. A lot of you probably have seen it before. Energy cannot be created or destroyed. It's always there. Energy is just transformed into other types. So we're going to look at a couple of the types of energy, and then we'll do a couple of calculations. And we'll have to use a little bit of the types of energy in order to do the calculation. There's only two types of energy we're going to worry about. We are going to talk about kinetic energy, and we're going to talk about potential energy. Potential energy is stored energy that could do work. Everything in this category is potential energy. Chemical energy, that's gasoline. So it's energy stored in fuel. Elastic energy is like bow and arrow. I know there's at least one person, I think, that uses crossbows in the class. Elastic energy, that tension that you get from your pull. My brother had a string go on his crossbow one day and just about had this enough energy. The more energy it has, the more force it has. And he was pretty lucky he didn't take any fingers off. So that's elastic energy. We see nuclear energy. New Brunswick, we're more familiar with that. They have a nuclear power plant. And gravitational energy is energy stored by lifting an object. If you want to think of it as a lifted object can do work because it can move a distance. So if you have a car hoisted, it takes work to lift the car. The work it takes to lift that car is related to the potential energy it has when it's lifted above the floor, above the ground, okay? So that's gravitational energy. We're going to do some calculations with gravitational energy. That's the only type. This is the only type of potential energy we're going to use in our calculations. It's the only one we need to worry about in our calculations. It's too complicated to calculate the other ones without, again, having you could have a whole year-long course on just physics and still not cover everything. Now, kinetic energy is energy that causes motion. Thermal energy, heat energy, is from moving particles. Mechanical energy is the one we're going to talk about, and that's energy that's moving. So a car changing speed, if a car is going at 60 kilometers an hour, it has energy from its motion. So that would be kinetic energy. Electrical energy is technically a type of kinetic energy. There's particles moving through a wire. Those particles are electrons, as we did in our last unit. And then you have magnetic energy, and that's just the energy caused by the push or pull from the attraction of magnets. There are a couple other forms of energy that are kind of hybrid. We kind of put them in their own category because they're special. Sound energy and light energy. Both of these require energy. If you want proof that sound requires energy, it doesn't take a lot of energy to power speakers, but it takes energy. So it takes energy to create that sound, and that's because those sound waves require motion and require vibration. So sound energy it requires energy as well, and light energy. And if you don't believe that sound requires energy, go crank your stereo loud enough, and you'll feel the energy that sound has. You'll feel that pumping if you're not familiar with that sound already. All right, so potential energy, it can do work, but isn't doing it yet. Kinetic energy is energy that's actually in motion. It's doing something. So this graphic is great to kind of show. Remember I said the energy can't be created or destroyed, it's just transformed. So I'm sorry this picture is grainy because I enlarged something that was small. So let's say you're on a bicycle, it could be a car. As you go up the hill, you have to put energy in. You have kinetic energy because you're moving. Once you get to the top of the hill, at that point, you are at a maximum height. You have the most potential energy you could have. All of the kinetic energy you have put in has converted to potential energy. It has the potential to pull you down the hill without you having to put in any more energy. So energy, you put energy into a system with the expectation that you'll get energy out. Does that make sense? Hopefully it does. One of a good example of this, my brother-in-law used to have, he had a Prius and he had a Leaf. I think it was the Prius that had, used to tell you your fuel efficiency. And I always kind of laughed because it reminded me of this picture. He lives in the Hunter River area. And we were driving to Charlottetown one day and he wanted to take us in the Prius to show us how fuel efficient it was. And we're driving along and he's talking about what the fuel efficiency is and how many liters per 100 kilometers he's getting. And we get to a part where we're going down a hill, we're coasting down a hill. He says, see, it's great. We're not using any energy. And I kind of had to chuckle at, because perhaps coasting down a hill isn't the best time to tell me how fuel efficient it is. Yes, it might be fuel efficient, but even my 100% gas vehicle is very fuel efficient going down a hill. Why? Well, I've put all kinds of energy in to get it up the hill. That energy is now converted to potential energy due to gravity. And when I'm coasting down the hill, the engine doesn't have to work as hard because gravity is working for me. So that always, whenever I think of this picture, I always remember him and his looking at fuel efficiency and telling me how efficient his car was as it's coasting down a hill. And I probably gave him a physics speech knowing me. I'm not 100% sure. He might, if he was spared, he was lucky, because I think of that every single time. But that's one of those scenarios. Even when we're on a trip, in terms of thinking about energy, the amount of fuel is an energy source. The amount of fuel you used is related to how much energy you have to put in. And if we're driving around PEI, it's relatively flat here. But I always notice when we go across to Nova Scotia, I get great fuel efficiency until I hit about the Cobequid Pass. For those of you that are familiar with that area, there's some substantial hills. And it's really interesting to watch how quickly those hill climbs, because I have to put a lot of energy in, those hill climbs make the fuel efficiency drop, I guess. Get less. I'll usually start out at about 12 to 15 liters per 100 kilometers. And after I've gone over those hills, I'm usually sitting around 10 to 11. So usually I'm about getting close to the 15 along the highway, especially in Nova Scotia. But then once you hit those big hills, your fuel efficiency drops. And that's because you have to put more energy in, but you're not maybe getting as much return on the energy outside. Anyway, enough of that. Sometimes I probably spend too long explaining things or trying to connect things. Sorry if I'm too long-winded. So think and apply. If energy is neither created or destroyed, why is energy transfer in an engine never 100% efficient? And if energy can't be lost, where does it go? First thing I notice when I pull my car into the garage is there's a lot of heat that comes off of it. And I maybe notice it more inside because the space is smaller. Heat is a form of energy. So if the car is giving off heat, is my energy all going into making the car move? No. The energy transfer is not 100% efficient in terms of motion. You lose a lot of energy in heat. Vehicles make sound, that loses energy. We get energy loss due to friction. There's going to be energy loss as it's converted into electrical energy. So all the different systems that are in your car are all draining energy so that 100% of our fuel does not go towards motion. So we're going to see that as we do a couple of calculations. Once we get to the end of our power section here, we'll do a calculation and we'll look at how many horsepower a car is supposed to have. And then based on some stats I found online, we'll figure out how many horsepower it's actually using, and we'll do an efficiency comparison. Is it 100% accurate? Not 100% sure, but we'll see. I think it's somewhere close. I remember a graphic I saw it. I couldn't find it again, but I think it's close. All right, so energy is not lost. It's just converted into other forms. So that heat, the hotter your car is, you got energy being lost. Think about it this way. Remember we talked about a sticking brake caliper before and how they get hot? and how that takes away from the forward motion. Well, that heat is basically friction. Friction converts to heat. It's taking away from the force that the engine can apply. Now, how do we calculate energy? So there's two formulas for calculating energy. We're going to use both of them. We'll just do a couple calculations with them. They're not hard to work with. Kinetic energy, energy due to motion, is related to the mass of the object times how fast it's moving. So 1/2 mv squared. Velocity is going to be meters per second, like we had at the beginning, so it's speed. Mass is in kilograms. Potential energy comes from how high the hill is. So how far above the ground an object is lifted. Mass, we have the acceleration due to gravity. M and G actually make up the force component, and height is the distance that the object could fall. Okay, so basically this potential energy will give us the amount of energy needed to lift an object. Kinetic energy will give us the amount of energy that's needed to move the object while it's in motion, and it doesn't necessarily have to be above the ground. Okay, so this is going to be object moving. This one is object not moving, just lifted up. The two are related. The energy it takes to lift the car while it's in motion, the change in energy as it moves, the total change will be equal to the energy it has once it's at its maximum height. So let's start with a calculation. How much energy is needed to jack a 1200 kg car to a height of 4.5 meters? Or 0.5, sorry, not 4.5, 4.5 meters. Okay, so 4.5 meters, I did a guess on that one. 0.45 meters. I figured it was about 18 inches and I guessed good. I just did a quick conversion just to see if I was close. So how much energy do I need? Well, we're lifting the object up. The object isn't moving. We don't have a speed, but we have a height and I have a mass. So we're going to use the equation where energy, it's lifted up, so it has potential energy, is equal to mass times gravity times height. Our mass is 1200 times gravity, which is 9.81 times the height of the object. Equals, I don't need a calculator, I have a calculator. 5297 joules. One of the reasons jacks are designed the way they are is they're designed so that you don't have to use, you don't use as much force, but use just as much energy in order to move the object. If you wonder how much work it is, this is how much work you would burn, or energy you would burn if you're lifting the car. Okay, so not too complicated to figure out. Mass times gravity times height. So that's potential energy. If you drop the car, you know it has a speed when it hits the ground. That would be kinetic energy. That would be equal to this total amount when it hits the ground. So you could actually figure out how fast it hits the ground if you wanted to. Next question, how much energy is needed for a 1,520 kg car to travel 17.5 meters per second? So we're assuming we're going from 0 to 17.5. So the kinetic energy is equal to 1/2 mv squared, which is half times 1520 times 17.5. And you have to square just the meters per second. Okay? And I'm going to double check that I actually calculated that right, because I left one number out when I was writing things down, and I don't know if, I want to make sure I put it in my calculator. And the kinetic energy is equal to 232,750 joules. So that would be traveling from 0 kilometers. That's how much the change in energy would be if you started at 0 and you went to 17.5 meters per second. Okay. If a passenger with a mass of 66 kilograms in the car, how much energy does the added weight of the passenger require? Well, how much energy is required just to move the passenger that fast? That's going to give us the amount of extra energy. So 66 kgs times 17.5 squared. Plug that in. And if you, for some reason, you don't get the same number, please let me know. And we get the amount of kinetic energy is only 10,106 joules. And really, this looks like a massive number of joules, but it's not really. If you look up how many joules of energy, energy is often listed in kilojoules. If you look on the back of a chocolate bar and how many joules or kilojoules of energy a chocolate bar has, it's actually kind of interesting. It's not really as much as you think. Now I'm going to just do, I'll do a really quick calculation here. I'll switch it to calories because if you're somebody that's familiar with calories, I can relate it to you for you. Of course, one time I want a conversion online. It's not a conversion I know by heart. There we go. So that would be the same as 55,000 calories. Okay, so by comparison, 55,000 calories is how much it would take, energy it would take to move a car from 0 to 17 meters per second of that weight. By comparison, the calorie intake that's recommended for most adult males is between 1,800, so 1,800 to 2,000 calories. So it's really not, like if you think about it, it's not that much energy in some ways. Anyway, I don't know if that was a calculation that was helpful or if it was just one of those things I was thinking in the moment as we're going through. The very last piece to calculate is power. Power is just how fast I can do work. So since work and energy, they're related to each other, the amount of energy it takes to do something is equal to the amount of work required. We can use work and energy. We can do two equations. We can use either work or energy, and we divide how fast energy can do work. So we take the work and we divide it by time, or we take energy and divide by time. You have to have your time in seconds. That'll give us power in watts, the same as electricity. It's going to give us work in joules and energy in joules. Now, excuse me, you know that typically with cars, we use horsepower instead, and 1 horsepower is 740. I rounded off to 746 watts. So we can use that conversion to do a quick calculation from watts to horsepower once we know that information. So we'll do a couple questions and then that patient finishes this section off. How many joules of kinetic energy does a 3,210 kilogram Corvette have if it's traveling 150 kilometers per hour? So it's going from 0 to 150. What's the kinetic energy change? So kinetic energy is going to be equal to 1/2 mv squared, which is half times mass, 3,210, times the speed. So we're going to use the meters per second speed. You always want to use meters and seconds. I'll try to remember to give you the conversion most of the time. And putting all of that into your calculator, half times 3,210 times 67 squared gives us 7,204,845. It's a big number, joules. Now we want to know how many watts of power are used. Well, power is equal to energy or work divided by the time it takes. So we're going to take that same number, 7,204,845, divided by 9.24. That gives us 7,204,845 779,745 watts. How many horsepower is that? If 1 horsepower is 746 watts, that's an easy conversion. 779,745 times, we'll do our conversion. So we've got watts. This is in watts. We want watts to cancel out, so we're going to put watts on the bottom. So we're going in this direction, so we're dividing. So we're going to divide by 746. And we're going to leave out question 4 because I had a question error and question 4 doesn't work out anymore. And we get 1,045 horsepower. Now, a Corvette does actually have a 300, the Corvette that the specs were given for does have a 350 horsepower engine. The issue with this particular question is how long was that energy applied over? So I can't do a straight comparison. So we're just going to leave that last piece out rather than me editing the actual question. Okay. One of the things that doesn't always get taken into consideration with some of these is there's all kinds of other factors in terms of this is we're calculating with this most simple scenarios just for kind of basics. But then when you actually know that you got a 350 horsepower engine, well, there's other things that get calculated in that. And I don't know how best I could relate all of them. So we just kind of cover some of the big pieces, but that allows us to do a quick watts to horsepower. So you would have used 1,000, just over 1,000 horsepower in order to go from 0 to 150. Okay. How much energy is required to lift a 7,280 kilogram truck to a height of 1.8 meters? So I'm assuming we have a hoist. How much energy do I need? So the energy needed is going to be like potential energy because we're lifting it up to a height. So 7,280, the energy it has at the top of the lift is going to be equal to the energy that was needed to lift it, times, we use 9.81, that's our G. So it's M times G times our height. So times 1.8. And we get that we need 128,550 joules. How many watts of power are used? So the watts of power is going to be energy divided by time. It's the same as work divided by time, which is equal to 128,550 divided by 5.24. And we get 24,532 watts. So how much horsepower is this lift, this hoist lift using to lift the truck? Well, we'll figure out how many horsepower. 34532 watts times, convert it, more horsepower, 746 watts on the bottom. These two would cancel near to simple division. I just left a number out. I wrote a 3 instead of a 2 when I recopied. Let's erase that and change it. There we go. Divided by 746 leaves me with 33 horsepower. So the calculations with power are really pretty easy. You find your energy or you find how much work. If you were given force and distance, you'd figure out how much work was done, and then you can convert that to how many watts of power. You can convert it to horsepower. They're all pretty simple questions. The very last question I want to ask is, if a car is rated for more horsepower, what does that tell you about how long it will take to change its velocity? How does physics prove it? Well, if a car has more horsepower, it's faster. Okay? That's going to be a faster car. It can accelerate faster. How does physics prove that horsepower has to do with faster? Well, horsepower is a type of power, and power is how much work it can do in how long. if it can do more work in a smaller amount of time, so if it can do more work in less time, it's going to have more power. That's how physics proves it. Power is related to time, and they're inversely related. Power's on the top, time's on the bottom. They make an inverse proportion. So if power increases, then the amount of time it takes to get the work done is less, which means your car is going to be faster. When we get to torque, we're going to find that torque is related to force more closely. Where torque doesn't have any time component in it. So if a car has lots of torque, that means it's going to have lots of pulling power. I shouldn't say the pulling power, actually lots of pulling force, but it doesn't necessarily mean that it can do it faster. So a couple little things to kind of think about. Horsepower is always related to how fast you can get the work done. So how fast you can accelerate is kind of one of your key pieces. So hopefully that gives you a decent background on the difference between work, energy, and power, and how the three of them are related in a way that you can kind of think about it in applying cars. Okay. The more force you have, the more energy you need, the more energy that's required to apply it, because work and energy are directly connected. And then the faster that you can apply that force, or the faster that you can use that energy, the more powerful your vehicle or your hoist or whatever it happens to be will be. So if you're working out at the gym and you want to show you have more power, you're going to have to lift more weight faster. There's an example for when gyms reopen eventually. All right, so that finishes off all of this section. For your assessment, we're going to look at a few videos, and I'm going to give you some notes. I'm going to get you to look at some videos and kind of do some describing scenarios with them. So it's not going to be all math. You will have a few math questions, but this section is going to be more kind of that think and apply, how can it connect to the real world.